So in this lecture, we're going to talk about inverse functions. So remember, a function is supposed to just be a way of, it's supposed to be a rule such that you give me this input x, and it's going to assign some value f of x. And it's only going to give you one output, right? So for every input, there's exactly one output. And the inverse functions, what those are supposed to do, if they exist, they only exist for one-to-one functions, but what they're supposed to do is they are supposed to essentially undo the action of f. So what you get here is this relationship which says the following. So if I were to think of f of x as a function, well, if it exists, it is a function from the set of values over here, and get back to my domain, what is the actual algebraic relationship that we get? Well, we get the following. We get that f inverse of f of x will get me back to x. Okay, so remember, f of x gets taken to some f of x, and then if I do f inverse, that's the inverse function of that output, I will get back to x. So that's sort of the algebraic relationship that I have. But I also have the composition in this way. Okay, so this is also supposed to be x. So in other words, that might look a little bit confusing, but this is also actually valid. It might be less confusing if I used a different letter here, like a y, but that letter choice is arbitrary. So this is also a valid equation that f and f inverse must satisfy. So for each of the following one-to-one functions, so again, this is one of the key features of why you would want a one-to-one function. It's where an inverse function exists. And when we look at the graph of inverse functions, I'll bring this up again. So the following are one-to-one, not asking you to prove that, but find the equations for the inverse function, and then write using this notation, the inverse function notation. So how do we do this? Well, what you do is, here's our function f of x. How do we find the inverse function? Well, first we're going to call this y equals 2x minus 5. And then what we're going to do is the following trick. We're going to swap x and y, solve for y, and then replace y with this inverse f inverse of x. Okay, one other thing I want to point out, this notation is reserved to mean the inverse function of f. It's not saying it's the reciprocal of f. Okay, so this is just the notation that is reserved for the inverse function of f. Okay, so let's just do this trick. That's what you're going to do for any time that you have to find the inverse function of a given function. Okay, so let's swap x and y. And what do we get? Just swap them. Okay, so wherever you see an x, make it a y. Wherever you see a y, make that an x. So you would have x is equal to 2y minus 5. And then now solve for y. All right, so let's do that. So how do we do that? We bring the 5 over here, so x plus 5 equals 2y, and then we'll have to divide both sides by 2. So then we will have y is equal to x plus 5 divided by 2. In other words, y is equal to x plus 5 over 2. And then the last step, will replace the y with f inverse. So here's your inverse function. Inverse of x is equal to x plus 5 over 2. And you see, you can actually check if the above is satisfied. You can actually either try to simplify that composition, or you can pick some values and actually see if it actually works. So let's say you plug in 0, for example. F of 0 would be negative 5. And then what happens if you take that negative 5 and you plug that in here? Negative 5, you plug that in. Negative 5 plus 5 is 0 over 2, which is 0. So you get back to 0. Right? Start with 0, get to negative 5, plug in negative 5, it gets you back to 0. So that's the idea. They kind of undo one another, right? undoes the F inverse will undo the action of F, and F will undo the action of F inverse. So let's try to find another inverse. So let's say we have f of x is equal to this rational function here. Now again, I've told you that it was 1-to-1, so you don't need to show that. So we know that an inverse actually will exist. So the key is first write out the function. Now let's swap x and y and solve for y. So this will be x is equal to y minus 2 over y minus 3. And now we have to solve for y. Well, how do we do that? Well, what we could do is we could try to multiply. So we would have, just multiply both sides by y minus 3. And then we'll have x times y minus 3. In other words, I'm sort of cross-multiplying here. If you write this as x over 1, just cross-multiply. But it'll reduce this y minus 3 in the denominator here, so we have y minus 2. So see, I'm just pretty much multiplying both sides by this y minus 3 to bring it over here. And now expand, so we have xy minus 3x equals y minus 2. And now we're trying to solve for y. So what do? Bring all the terms that have a y to one side and bring everything else to the other side. If you remember back for solving for particular variables, that's always the procedure. Bring everything that involves that variable to one side. So I'm going to bring this y over here, and I'm going to bring the 3x over here. So we have 3x minus 2. And then now we'll factor out the thing we're solving for, which is y. And then now we divide both sides by this x minus 1. And we get y is equal to, these reduce, right? 3x minus 2 over x minus 1. And that's our inverse function. So inverse of x, f inverse of x is equal to 3x minus 2 over x minus 1. And again, if you want to check the original algebraic description is satisfied, these compositions would essentially cancel each other. But say you pick some input. Say try 0 again. So 0, 0, you get negative 2 over negative 3, so 2/3. Then plug in 2/3 over here. So 3 times 2/3 is a 2. 2 minus 2 is 0. So 0 in the numerator, and the denominator is not 0. So we get 0 back. So you see there, input 0, you get 2/3. Input 2/3, you get back 0. So you see how they're kind of undoing the action of the other. But that's how you solve for them. So now let's say f of x is 1/2 x plus 5. You could figure out the inverse function, but I'm giving it to you right here, 2x minus 10. You can check that those are actually inverse functions of each other, and then use these two functions to just find the following evaluation. So let's just do that. So f of negative 4, well, f of x is right here, so we will just plug in negative 4 and simplify. So this will be negative 4 over 2, so that's negative 2 plus 5, so this is 3. And if you want to check, actually, what happens if you plug in 3 into the inverse here? So then you'd have 6 minus 10, so that would be minus 4. So you see we get back to what we started with. So for at least that value, it looks like it's agreeing with what the inverse should be. Okay, let's figure out what f inverse of negative 4 is. So plugging in negative 4 up here, we have 2 times negative 4 minus 10. That is negative 8 minus 10, so that is negative 18. Okay, and just as sort of an interesting check, if you plugged in negative 18 into f, what would you get? You get negative 18 over 2, which is negative 9. Then you add 5, you get negative 4. So you see you get back what you were plugging into the inverse function. So you see these are behaving like inverses as they should. Okay, now what about this? Well, you're doing f of f inverse, and so these annihilate each other, okay? When you're doing f of f inverse of something, you're always going to get back the input, which is negative 4. Okay, solution 2, which is the long way, is not believing that they annihilate one another and just slowly simplifying it. So what would this be? Well, we already figured out what f inverse of negative 4 is. It's right here. Negative 18, right? This is right here, negative 18. And what is f of negative 18? Well, you come up here and you plug in negative 18 like I already suggested we should do. Negative 18 plus 5. You will get negative 9 plus 5, so that'll be negative 4. So you see, I already got the same answer. Okay, what about f inverse of f of something? Well, they are going to annihilate each other, so I will get this input of negative 4 again. Okay, solution 2, let's see if that actually is true. Well, I suggested we actually do that before anyway, so we're gonna see that it works. So what is f of negative 4? Well, we figured that out already. That is right up here. It's 3, right? So then that would be f inverse of 3. And then you would plug that into f inverse. So 2 times 3 minus 10. So 6 minus 10 is minus 4. So it looks like we're correct, either remembering this property or just doing this the long way. Okay, now moving on. Given f of x is 2x plus 4, let's find the inverse, and then let's graph both functions. Okay, so how do we figure out the inverse? Well, y is equal to 2x plus 4. We will swap and solve for y. Okay, so swapping them, you have x equals 2y plus 4. So then we will do x minus 4 equals 2y, and then we will divide both sides by 2 to get y is equal to this right here, x minus 4 over 2. Whoops, that 4 always looks like a 9 if you write it too quickly. And then that's x over 2 minus 4 over 2, which is 1/2 x minus 2. Okay. And this is the inverse. So this is inverse is equal to 1/2 x minus 2. The only reason I actually simplified it a little bit was to show you that it's also a linear function, right? The original one is a linear function, y equals mx plus b. There's your slope, there's your intercept, and over here we get another linear function. So let's graph these. The first one, if the slope is 2 and the intercept is 4, so 1, 2, 3, 4. There's the intercept for f. The slope is 2, so here's a point, here's a point, here's a point, here's a point, and so on. Let's connect these as best as I can. Okay, so there is f of x. Okay, and then how do we graph the inverse? Well, just follow the same procedure. You have the intercept at negative 2, but the slope here is positive 1/2. So we're only going to rise 1 for every x of 2, right? So here's another point, here's another point, here's another point. So you see that they actually intersect at that point right there. Okay, so there's f inverse. And now at this point I can point out a very neat feature that inverse functions and the original function share. So f and f inverse, if they both exist, right, are symmetric about the line y equals x. Okay, so what is the line y equals x? Well, that's a line that has slope 1, intercept 0, right? So that is this line right here. Y equals x. So going down very carefully. Okay. Do you see that if I were to put a mirror on this red line, do you see that they're symmetric about that line? Every point has a corresponding point right through the line y equals x, and that's specifically because the way that you find them is you swap x and y and you just solve for y. So that swapping procedure is exactly giving us that symmetry involved. Yeah, so this feature is extremely important to understanding the geometry between f and f inverse, and that could be quite helpful actually, especially if you have kind of complicated inverse functions. All right. One last feature I just want to point out that I mentioned up above is remember that inverse functions are only going to exist for one-to-one functions. And you can kind of see in this picture, f is, it's a function, it passes the vertical line test, but it's also one-to-one, right? It passes this horizontal line test. And in order for you to be able to have this type of symmetry, that is what is this property of having the horizontal line test also be satisfied is allowing you to have the symmetry so you can do this swapping, but then also have a function after you do so. Okay, so we want to make sure that what we get in the end after doing that swapping is actually a function. So passing the horizontal line test would become passing the vertical line test for the inverse function, meaning it's actually a function. Okay, so that's a little extra information, but a reason why we would require the functions to be one-to-one in order for an inverse to exist.